The presentation of the standardization and research on fracture of polymers, polymer composites, and adhesives within EASY TC4 is divided into 4 parts. After a brief history and how EASY TC4 operates, test standards that have been developed so far are briefly presented, then fracture test procedures that are currently under development, and the main focus of the presentation will be on open questions and issues that likely will become future topics of activity within TC4. Technical Committee 4 was founded in 1985 by Hans-Henning Kausch and Gordon Williams and was chaired since 1989 until 2017, jointly by Gordon Williams and Andreas Pavan. There were semi-annual meetings since 1986 with between 15 and 35 participants each, 8 conferences with 90 to 120 participants each. There were 2 books published on fracture mechanics and numerous review and research papers. But there were also several fracture test procedures that were developed through round-robin tests and submitted to I. Typical standards development works starting from scientific work in combination with an industrial need. Then a test procedure called a protocol is drafted. This protocol is then evaluated in a round robin with a mix of academic and industrial participants in order to evaluate the protocol and in particular aiming at low interlaboratory variation. This first round robin usually leads to refinement of the protocol, followed by additional round robins, also dealing with alternative materials of the same class, for example with higher toughness, to make sure that the procedure is applicable to a sufficiently wide range of materials. And if successful, then a draft document is prepared and submitted to ISO as a new work item. Test standards have been developed so far. We look here at those for plastics only, highlighted in red. There is a quasi-static fracture toughness test procedure, a tangent-tangent fatigue crack propagation procedure, and one fracture toughness at moderately high loading rates, around 1 meter per second. There was also an amendment drafted that deals with testing of plastics containing short fibers. This has been withdrawn and replaced in the quasi-static and moderately high loading rate procedures as an annex. So these can be applied to plastics and plastics containing short fibers. Fracture test procedures on development comprise a peel test for flexible packaging laminates, the determination of fracture toughness of thin films and sheets with the essential work of fracture approach. And for example, for fiber-reinforced plastic composites, there is determination of mode 1 interlaminar fracture toughness under cyclic fatigue fracture loading. 2 round robins have been completed, and the third one is now in progress, looking at an alternative procedure. And this procedure was required because of issues, namely that the test standards specify unidirectional fiber orientation of the specimens, and then in the test these may yield fiber bridges. Examples are shown in the photographs here, and these fiber bridges between the 2 arms of the specimen then have an effect on the measured data in the so-called resistance curve. This is basically energy release rate plotted versus delamination length, and this is steadily increasing due to this fiber bridging. And depending on what the data will be used for, these fiber bridging effects have to be accounted for. And currently there is a round robin using a proposed methodology by Yao et al. The reference is shown here. One of the reasons is if these fracture data are used in structural design where less or no fiber bridging may occur depending on the layup of the composite. And one example is shown here, a fairly complex part that failed more or less unexpectedly because of crack propagation that was not affected by fiber bridging. This procedure will now yield a set of curves that can then be extrapolated to a predicted upper bound fracture growth curve And this is described by the equation shown here that contains the threshold value GDHR here as an explicit parameter. So the threshold can be evaluated with this so-called modified Hartman's-Keibe equation quantitatively, and also the scatter typically in these curves can also be assessed, and then this will provide safe design limits for composite structures. Fracture modeling in composite structures requires materials data, of course. These can be obtained, for example, with a test like this, a 4-point bending test in cyclic fatigue, propagating the delamination from the right-hand side of the specimen. And then these data can be used in finite element modeling to predict occurrence of delaminations, shown here. But recently there was a proposal to look into smarter testing using extensive simulation to reduce the design and experimental validation effort, and hence save time and money in the design and development of composite structures. Another issue is the effect of environmental exposure on polymers and polymer matrices in fiber-reinforced composites. For example, a polymer specimen in a 3-point bend configuration can be exposed to a specific environment, a fluid, for example, and for the case of polyethylene, the curves clearly differ whether the specimen is exposed to air or such a fluid. Similarly, for polystyrene, again, quite significant difference between these two curves depending on what the ambient medium is. And for polyethylene, also shown here an example for exposure to chlorine oxide, and then the strain at break can be evaluated as a function of exposure time, and then yields curve that yield information about the long-term durability of these materials. Also, digital tools are becoming more and more important in experimental fracture mechanics research. Initially, it started with digital data acquisition of the test machines so many years ago, and then the use of spreadsheets for the data analysis. One example is shown here, but now there is digital imaging during test and image analysis that will replace the visual observation shown in this photograph here. And also data fitting routines can be used to determine, for example, the nonlinear point in a load displacement plot or the 5% change in compliance. And so far, no standards or guidelines yet are available defining minimum requirements for these different digital tools, for example, with respect to resolution and sampling. And of course, the question is whether in the future this can be developed into a fully automated test and analysis. Interesting question. And as a summary and outlook, EasyTC4 has successfully developed fracture mechanics test standards and will continue to develop and validate such procedures. One focus is on the applicability of the data generated by the tests in structural design and looking into effects of environmental exposure. Digital tools are clearly expected to help reducing the scatter in experimental data and to minimize operator-dependent effects. Modeling and simulation in the future are considered essential for reducing test efforts and cost in structural design and development. And fracture test procedures for other classes of polymeric materials of engineering interest, for example, elastomers or soft materials such as foams and gels, are under consideration. And an important question is also whether new manufacturing methods, for example, additive manufacturing, may require new tests or new approaches for analysis, for example, due to the different defect distributions that are generated by these processes compared to more conventional processing. The final message is anyone interested in these activities is welcome to contact the secretary or the co-chairs of EasyTC4, And more information on the activities, meeting dates and contact details are available on the website of ECTC4 that is shown here. A few acknowledgements. This presentation is based on contributions from many past and current members of ECTC4. Special thanks go to the ECTC4 session leaders who have developed protocols and organized the round robins, and specifically also to Andrea Pavan, John Alan Pascoe, Masaki Hocho, and Rhys Jones for suggestions and discussions. And we thank you for your attention.